Welcome to e-Padasala lecture series in computer science. So, in this module we are going to discuss about the brute force technique. Remember, we started the brute force technique last module where I said brute force technique is one of the most primitive design technique in algorithms. Using the technique we discussed about solving problems like linear search, bubble sort and selection sort. In this module we are going to concentrate on two important problems. One is the closest pair problem and another is the convex hull. The objectives of this particular module is going to be to understand the concept of closest pair problem. So, we are going to discuss about the convex hull problem, where we are going to discuss about the applications of the closest pair convex hull algorithms, and also we are going to discuss about how to generate the convex hull for a given set of points. Recollect, last module we discussed about the brute force technique. So, I was telling you that it is one of the most primitive and straightforward approach for solving the problems based on the problem statement and the definitions as part of the problem statement. So, we will just apply that technique for the closest problem, closest pair problem. This is a very famous problem. So, the problem can be stated like this: given a set of points in a plane, the point can be cities, it can be transistors on a circuit board, or it can be computers on a network, etc. Given this set of points, we have to find the closest pair of points. So, this is a very interesting problem which has been given in computational geometry. So, this problem we will encounter in algorithm study in a number of ways. Fine. Let us try to give you a formal statement for this particular problem. The formal statement is like this: we are given n points that can be present in 2-dimensional or in k-dimensional space. So, what we have to do is we have to find the closest pair of the points that are present. So, to find the closest pair, we have to use a distance measure. In mathematics, the closeness or the farness of points is measured in terms of distance. So, we have to compute the distance between each pair of points, and then we have to identify the points whose separation distance is very small. In other words, formally the problem can be stated like this: we are given n points and we have to find point P and Q such that the distance between P and Q is minimum. Fine. Suppose if this is what the problem is, how we are going to solve? The solution outline is going to be like this: we have to compute the distances between the points, and we have to select the point whose distance is going to be very minimum. This is what the solution outline is going to be. Fine. How we are going to measure the distance? In other words, what is the distance measure we have? In geometry, the distance between 2 points can be measured in number of ways. One way of measuring the distance between the point is by Euclidean method, and that distance is called the Euclidean distance. Suppose let us assume that we have 2 points P of x comma y and Q of s comma t, where this x and y are nothing but the coordinate positions of points. If this is the case, then the Euclidean distance between the points P and Q can be computed using this particular formula. So, you can see very well the Euclidean distance between the point P and Q is nothing but the root of x minus s whole square plus y minus t whole square. You have to take root of these two. So, this is what we are calling as the Euclidean distance. The Euclidean distance will give numbers that may be the fractional numbers also, because we are taking root of a number, therefore, it can be a fractional one. Sometimes dealing fractional numbers takes lot of computational time. So, therefore, solving these problems using Euclidean distance can be very time consuming. In that case, perhaps we can go for some other distance measure. One distance measure is called the D4 distance. D4 distance is also called as the city block distance. So, the city block distance between the points P and Q can be defined as something like D4 of P comma Q is nothing but x minus s and y minus t. So, you can see very well there is no root of symbol here, therefore, this will be less computationally intensive compared to the Euclidean algorithms. Another distance is called D8 distance. This is also known as the chessboard distance, and the formula for computing the chessboard distance is going to be like this. D8 of P comma Q is going to be the maximum of x minus s and y minus t. In other words, we are still more reducing the complexity of computing distance by taking the maximum of x minus s and y minus t. We can generalize this. We can generalize all these formula as the Minkowski's distance, and the Minkowski distance can be given like this. So, this is the generalization of the previous formula which we have studied, and if we substitute p equal to 1, we are getting the Manhattan distance between the points, and when p is equal to 2, then we are getting the Euclidean distance between the points. So, now the problem is well defined. Now, we are given n points and we have lots of distance measures, then we have to find the smallest distance. So, I am taking one simple example. Let us assume that we are given 2 points P and Q, and the coordinate position of P is going to be 10, 10, and for Q it is 10, 0. If this is the case, then I can find the Euclidean distance using the formula that we discussed. It is nothing but the root of 10 minus 10 whole square plus 10 minus 0 whole square. So, you can see very well it is going to be 10. So, that means it is 10 units. It is not having any measurement like millimeter or centimeter. It is in terms of pixels in the case of images and video, and we can simply say that it is 10 units. Similarly, D4 distance can be computed as 10 minus 10 plus modulus of 10 minus 0, it is going to be 10. Similarly, D8 distance is going to be the maximum of 10 minus 10 and 10 minus 0, which is going to be 10. Incidentally, for this problem all these distances are coming as same, but it need not necessarily be so for all circumstances. In some cases it may vary also. Fine. This distance measure we can call as a metric if these properties are satisfied. Suppose let us say if 2 points A and B are given, then if distance between B and A is similar to the distance between A and B, then we can call that as the symmetric property. Similarly, the distance between the point A comma A is going to be 0, and this property is called the constancy of self similarity. and distance if it is greater than or equal to 0, then it is called the positivity property. Similarly, the distance between A is lesser than or equal to distance between A to C and the distance between B to C. This property is called triangular inequality. In short, we compute distance measure, and if the distance measure satisfy all these properties, then it is called the metric distance or simply as metric. Fine. So, now we will put all our ideas into a informal algorithms. Now, as I said earlier, we are given n points. So, let us take one point I of the set S, and I am taking another point j of the set S. Then I have to ensure that both the points are not same. In other words, the points I and j should be distinct. So, now I have to compute the distance between I and j using any method. Say for example, I am using a Euclidean distance, means I have to use that formula to compute the distance between I and j. Suppose if distance between I and j is going to be the minimum distance, then we have to update the distance between the points I and j. Then I am starting a loop, then I have to consider all points that are present, and in that case find that minimum distance will be computed at the end of the loop, then that is going to be returned to the main algorithm. This is the informal algorithm we have. Fine. So, we can think of writing in a formal manner. To simplify the task, perhaps we can do one thing. We can sort all the points based on the coordinates in an ascending order. Why should we do that? The reason is like this. We are going to store all the points in an array, and then we are going to check the distance between the points. So, we do not want to store that in an unordered manner, and the another advantage is if we store that in the ordered manner, then I have to compare only the adjacent points. So, because of this particular reason, so in step 1 I am going to sort all the numbers in the ascending order. So, for that I have to use an algorithm. Suppose if I am using merge sort or something, I will get the complexity as order of n log n. Then after that I have to compute the distance between the adjacent points or numbers. In that case the complexity is going to be theta of n, and I have to update the smallest one, it is going to be theta of n. Therefore, if you see the complexity of all the things, it is coming as order of n log n and theta of n and theta of n, which is going to be order of n log n. So, this is what the formal algorithm is going to be. You can see very well what we are going to do is all the informal algorithm we are going to conceptualize this as a formal algorithm. You can see very well we are giving the keyword algorithm, and this is going to be the brute force closest point, and we are going to give a list of n points as a list P. So, you can see very well initially d min is going to be infinity, then I am starting the loop. So, now everything is going to be in the sorted order, therefore, I am starting the loop from 1 to n minus 1, and another loop I am starting from j plus 1 to n. So, that means I am going to compare only the adjacent elements of this particular array. So, therefore, I will compare the first element with the second element with the third element, etc. So, that means now for these points I am going to compute the Euclidean distance, and that Euclidean distance I am going to store as part of D, and already I initialize d min as infinity, and if this d is going to be lesser than d min, then I am going to update the minimum distance, and also I am taking the note of that particular point I as well as j. So, this will be repeated in a loop actually, and when we consider all the points, then we will come out of this particular loop. In that case, what is recorded in index 1 and index 2 are nothing but the points for which what you say the distance is minimum. Therefore, we are returning this point index 1 and index 2. In other words, this is the formal algorithm of the closest pair. Fine. How to analyze this? Recollect the module where we discussed about the iterative algorithms, where I said we have to find the basic operation and then we have to see how many times the basic operation is repeated. So, now you can see very well in the algorithm we have started a loop from I equal to 1 to n minus 1, and inner loop starts from I plus 1 to n. So, under that we have to put the basic comparisons. What is the basic comparison? Basic comparison in this case is going to be the computation of the Euclidean formula. So, that means we are performing the minus and then we are performing the root. So, that means two operations are there. So, now this is what you say the number of operations that are done as part of that particular loop. 2 is a constant, therefore, I can take it outside. So, it becomes what you say simplification of this loop. So, if I simplify this, then it will become n minus I plus 1 plus 1. So, it will come to n minus I, and if I simplify this, you can see very well I is replaced by 1, 2, so on. When it becomes n minus 1, it becomes 1. So, now you can see very well this is nothing but the Gauss formula. Gauss formula you know very well is 1 plus 2 plus 3 plus 4 plus up to n is nothing but n into n plus 1 by 2. It is one of the most influential formula that is useful in counting purpose. So, now you can see very well 1 plus 2 up to n minus 1 is nothing but n into n minus 1 by 2. 2 get cancelled, finally it becomes n into n minus 1. You can see very well it comes as theta of n square. In other words, in the best case, average case or worst case, the number of points that needs to be considered are all the points. Therefore, the complexity of this algorithm turns out to be theta of n square. It is not the efficient one. So, later on we are going to discuss that using a better design technique like divide and conquer, we are going to solve this in theta of n log n time, but nevertheless this is what the brute force technique algorithm for solving this problem is all about. The next interesting computational geometry problem that we are going to consider is called the convex hull. So, convex hull is a very interesting problem where we are given a set of points S, and just imagine all the points as pegs. Then if that is the case, then we can say convex hull of S is nothing but the shape of the rubber band stretched around the pegs. In other words, we can say convex hull is the smallest polygon that is available to encompass all the points of this. The formal definition can be given like this. The formal definition is convex hull is the smallest convex polygon that contain all points of S. This is the formal definition of convex hull. So, you can see very well this is the example of a convex hull. These are various points that are given. So, you can see very well the closest polygon that can be approximated is by connecting all these points to get this. So, you can see very well these are the extremal points. These points are called extremal points, and these points form the vertex of the boundary of all these points. these internal points are not very much important for convex hull and these can be omitted. In other words, convex hull is all about finding the extremal points such that they can be connected by the line, and that boundary should encompass all the points of this particular set. This is what we are calling as the convex hull. This is another example. So, you can see very well these points are given, and the position of these points in a two dimensional space is given. So, now what we are going to do is we are going to find the smallest polygon. That smallest polygon is going to be like this. Now, you can see very well this P4, P9 etc. are forming the vertex of the boundary. In other words, these are going to be the extremal points, and these inner points P1, P3, P6, P7 are not very much important. Fine. You may wonder what that convex is all about. Why we are saying this as convex hull? The reason for that is very simple. The formal definition of convex is it is a polygon with no indentations, and we can say a polygon as a convex if every line segment that connects the interior points lies within the polygon itself. For example, we can call this polygon as a convex polygon because I am taking 2 points P and Q and I am connecting this by a line segment, and you can see very well this line segment falls completely within this convex. So, therefore, I can call this as convex, and this is not convex because if I take points P and Q, you can see very well this lies outside the polygon. Therefore, I can say that this is not a convex polygon, but concave polygons. So, that is the reason why we are intending to find the convex hull for the set of points. Why should we do that? The reason is like this. For us the importance is not very much, but for robotics field this is very much important. In robotics the intention is to find the convex hull, in short to find the shortest distance between the objects such that the collisions can be avoided. Convex hull is one of the most important problem that is used in the domains like robotics and games. Even in mobile computing, convex hull is very important because we can say given some n cities as points, we can think about where to put towers, etc. So, typically the tower will be put only in extremal point. For that the convex hull needs to be constructed. Fine. The whole problem is now reduced to find what is the extreme points. An extreme point is a point of the set that is not the middle point of any line segment that can be constructed. In other words, take any points, draw a line, and if any point that forms the midpoint of that particular line, then that point is not going to be an extreme point, but it is going to be an internal point that can be avoided. So, that means now the whole problem becomes finding the extreme point, and extreme points now becomes the vertex, and if I keep on connecting all the vertex together, then I am getting the convex hull of that. Fine. So, the logic is very simple. I will take 2 points P I and P j, then what I am going to do is I am going to construct the line, and if all the lines are forming what you say on one side of the line, then I can call that as a boundary, otherwise it is not the boundary. That is the logic I am going to follow. This simple idea is what we are going to use as part of the brute force technique. In other words, in brute force technique, what we are going to do is we are taking 2 points and then we are going to construct a line, and then we are going to check whether all the points are on one side of that particular line. If that is the case, I am going to decide that it is going to be a boundary, otherwise it is not a boundary point. So, in short, formally if two points are given whose coordinates are x1 y1 and x2 y2, then you know very well this is the line equation. So, that means you can see very well the coordinate plane can be defined by this equation ax plus by is equal to c, where this a is nothing but the y2 minus y1 and b is nothing but x1 minus x2 and c is nothing but x1 y2 minus y1 and x2. In other words, this is the what you say equation that going to define the straight line in the coordinate plane. So, now this line is going to divide the entire plane into two half planes. So, that means in both the sides we are going to points. So, that means if x1 ax plus by is going to be c for one set of points, while for other points it is going to be ax plus by is going to be less than c. As I said earlier, if all the points are on one side, then it is going to be the boundary, otherwise it is not. So, in other words, the algorithm can be conceptualized like this. So, I am going to find the pair of points p1 and p2, and I am going to determine whether all the points are on the same side or not. In other words, whether this ax plus by minus c, I am going to check whether it is having the same sign or not. So, this is what I am going to do as part of this particular algorithms. Fine, I am conceptualizing this into a formal algorithm. You can see very well it is algorithm slow convex hull. P is nothing but the set of points that are given, and what I am going to do is I am going to construct the convex hull. So, you can see very well. So, I am going to draw a line, you can see very well, and I am going to check whether the points are on the left. If that is the case, fine, I am going to what you say add that as the boundary, otherwise it is not so. Fine. The complexity analysis of this algorithm is going to be like this. So, how many pairs of lines are there? The pairs of lines are going to be what you say n square minus n by 2 pairs of lines are there, and I have to compare that with n minus 2 other points. So, naturally you can see very well the complexity of this is coming as big O of n cube. So, you can see very well this is a very high complexity, because to convert that geometric insight into an algorithm in a brute force manner requires so many comparisons. In short, the efficiency of this algorithm is going to be what is a theta of n cube. Again, as I said earlier, brute force is not leading to an efficient algorithm. Therefore, this too is not a very efficient algorithm. Later on we are going to discuss about various other techniques where we are going to discuss about construction of convex hull in a much faster manner. In short, I can summary this particular module like this. Brute force technique guarantee the solutions, but the algorithm that we are going to get is not very efficient, and closest pair problem is one of the most important problem which is encountered in algorithm study very often in computational geometry context. This can be solved by the brute force technique, and the complexity of that particular algorithm is going to be order of n cube. Similarly, convex hull is another important algorithm that is encountered in algorithm study in the context of computational geometry, and the brute force algorithm what you say, leads to an algorithm that is having the complexity of big O of n cube. In short, we can summarize the whole thing like this. Brute force algorithm is one of the most primitive algorithm design technique. It does not give any efficient algorithm, but nevertheless the algorithms can be used as a benchmark for comparison purpose. So, in this module we discussed about two problems. So, in the next module we are going to deal with some more interesting combinatorial problems as part of brute force technique, and these constitute the foundation of algorithm that we are going to discuss in the future modules. Thank you very much.